Okay, we're going to talk a little bit about graphing tangent functions. And to get started, I want to talk about a few things that we know about the tangent already from our study of the unit circle and trig in general. Probably the most beneficial right off the bat is that we can always recognize that tangent of x can be written as the sine of x over cosine of x for virtually any angle. Not virtually, any angle. So we're going to study the tangent graph in thinking about the ratio of the sine to the cosine, thinking about it like a rational function, and some basic fundamentals that we know about rational functions. Like, for example, when the denominator is equal to 0, that's going to cause a vertical asymptote. However, when the numerator of a function is equal to 0, to think about anything where you have 0 divided by anything, 7 or whatever, that answer is going to be 0. So one of the key things that we're going to say is whenever the denominator, that is cosine of x, is 0, we're going to have a vertical asymptote. And whenever the numerator sine is 0, that's when we're going to have an x-intercept or a 0 y value. But even more fundamental than that, we're going to talk about what the pattern is for tangent. And we're going to think about the period of a tangent function. And so I've got a little unit circle up here, and we're going to think about the nature of why sine and cosine have a period of 2 pi. Because if you think about, say, for example, the cosine of an angle, when you're over here in the first quadrant, the cosine, of course, is positive. And as you move to the second quadrant, the cosine goes negative because we're measuring the width of our triangles. And once we get to the left side, we're going to get negative cosine values. Down in the third quadrant, of course, we're still to the left side. Anything on the left side, the cosine is going to be negative. And then when we get back to the fourth quadrant, the cosine goes positive. So you can kind of think of the pattern for cosine as positive, negative, negative, positive. And then as you move around the circle again, it's just positive, negative, negative, positive. So for every 2 pi, you're going to start, it's going to take 2 pi before it starts to repeat itself. Positive, negative, negative, positive, positive, negative, negative, positive, and so forth. Sine, on the other hand, starts out in the first quadrant as positive because we're in the upper half and the sine is always measuring the y component, the y coordinate. In the second quadrant, it's positive again because we're still up top. Then when you go down to the third quadrant, it's negative, and in the fourth quadrant, it is negative. So sine has this pattern of being positive in the first 2 quadrants and negative in the second 2 quadrants. Positive, positive, negative, negative, and so forth. So you can tell that for both of these, it takes a full trip around the circle before they start to repeat each other. But if we think about tangent as being the sine over the cosine, think about these ratios and think about taking the y value and dividing it by the x value. A positive divided by a positive would be, of course, positive. So the tangent in the first quadrant would be positive. In the second quadrant, we have a positive divided by a negative, and so that's going to give us a negative ratio. So the tangent in the second quadrant is negative. Down in the third quadrant, and this is where it gets interesting, we have a negative divided by a negative, and of course that gives us a positive ratio. So in the third quadrant, we're back to being positive. And then of course in the fourth quadrant, we have a negative divided by a positive, and that brings us back to negative. And it's just going to keep repeating that positive, negative, positive, negative, positive, negative. But if you think about the nature of periodic functions, we're asking, like, how long does it take before it repeats itself? Well, you can see it repeats itself after just 1 pi, or just half a trip around the circle. So the period of a tangent function, unless it has a value that's being multiplied by, a constant that's being multiplied by the variable, is just going to be pi. So in terms of something like the tangent of 3x or something like that, we might think of a function as like 4 tangent 3x. This will be the a value, and this will be the b value. So we have functions that look like a tangent bx. The formula for the period is going to be, and we'll make a big note of this, period for tangent is going to be pi over b. So now we want to look a little bit at what's going to happen to the graph of tangent as we move through the unit circle. But let's just think about sine in this first quadrant as it goes from a y value of 0 up to a y value of 1 by the time it gets to pi over 2. So, you could think of, I guess we'll put a y value of 1 there. And so it starts at 0, and by pi over 2, it gets up to 1. So we're going to look at something like that. And of course, if we continue on over to the second quadrant, sine gets back to 0 by the time it gets to pi. So, of course, by the time sine is back over to pi, the y value comes back down to 0. So with that in mind, you think about anywhere the sine is 0 because it's the numerator of the tangent function, the y value of tangent is going to be 0. Similarly, though, now we want to think about cosine. And a cosine curve, I'll do this guy in blue. Cosine curve, of course, starts at its max y1, and by pi over 2, it's down to 0. So a cosine kind of comes down like this, and then we'll proceed on and go to -1 by the time it gets to pi. So by the time cosine gets out here to pi, it's down to y value of -1, which of course we can see as we get over here. What's interesting is, of course, you certainly should remember that they're equal to each other at pi over 4. Both values are √2/2 for both the sine and the cosine, so that's where they intersect. But now you think about, okay, well, the place where this cosine is equal to 0, that's right here at pi over 2, you're going to have a fraction with a denominator equal to 0. And of course, that means your function is going to have a vertical asymptote. So let's indicate a vertical asymptote with like a big yellow vertical line. And I'm not going to take the time to do it, but I think you could see if we had gone to an angle of -pi over 2 back over here, again, the denominator is going to be 0 and the numerator is going to be -1. That's going to create another vertical asymptote. So a tangent is going to have vertical asymptotes at -pi over 2 and pi over 2. And interestingly enough, the tangent curve, again, as far as one other reference, well, we of course have this place where at x equals 0, I'll make my tangent curve green here. When the sine is 0, the tangent will also be 0. So right here at the origin, the tangent's going to have a graph. It's going to have a value of 0. And at pi over 4, where the sine and the cosine are equal to each other, the tangent's going to have a value of 1. So I'm going to put a little 1 there. As we go to this back side of this thing, that would be -pi over here, -pi over 4. I should probably add a little negative sign here. At -pi over 4, that's over here, down here, the tangent would again be negative, but it's going to be -1 because at this point down here at -pi over 4, we could think about it being √2/2 for the cosine, but -√2/2 for the sine. And of course, if you put this over this, you're going to get -1. So we have a y value of -1 here. So the tangent curve has this kind of look almost like a cubic function where it kind of comes up here and then it blows up, but it's literally going to blow up to infinity as it gets close to that vertical asymptote, and then it's going to repeat itself over here just in the negative direction. And so that green shape that we have right there is the basic look for a tangent curve with a period of 1 full pi, because we start over here at -pi over 2 and we finish at pi over 2, and that distance of course would be pi. The distinguishable points that we have are not many. We just have the point at pi over 4 comma 1 right there, pi over 4 comma 1, and then we have this other point here at -pi over 4 comma -1, and then of course the origin at 0, 0. So that's our template for a basic tangent curve. It kind of looks a little bit like a cubic function that it goes up through the origin, except it comes into a vertical asymptote as opposed to just kind of growing more quickly. If you wanted to repeat this tangent curve would again start to go like this, and it would come up here and just repeat another one of these patterns that it has going on in this first thing, and it would go off in the same way. Similarly over here, it would have a similar look and just kind of keep going that whole way. So there's a basic tangent curve. So now we can work an example of a tangent curve that has an a value and a b value that aren't just 1. So we can get a sense of what these problems might look like from a textbook for a homework or on a test or a quiz. So I like to list my a value and my b value, and as soon as I list the b value, I'm going to think that the period for tangent, and this is the big one that many students forget, is that the period for tangent is simply pi over b, which in this case would be pi over 4. And again, that's the entire length of a tangent curve that does its run. So as a basic tangent kind of has this look to it. The right side, this total distance that it's going to take for it to do its thing is going to be pi over 4. I find it useful to figure out what half the period is, which in this case would be half of pi over 4, yikes, which would be pi over 8, of course. So half of pi over 4 is pi over 8. And even if you want to go so far, we could say 1/4 of the period. That'll come in handy as well. 1/4 of our pi over 4 is, of course, pi over 16. Now, what we have to realize with the tangent curve when we start to graph it is that half the period is going to be on the right side, moving up like this toward a vertical asymptote, and the other half is going to be down here, unless we have a negative sign out in front of this, in which case it's going to get reflected. But for right now, we'll just take this idea like that, and we will move from there and say, okay, we need to have half the period on the right, so that's going to be pi over 8 over here, and we need to have the other half, negative pi over 8, on this left side of the y-axis. It's negative pi over 8. Now, our quarter marks are going to be important as well. This is pi over 16 and negative pi over 16. And all we have to do now is remember that we're going to be framed in by vertical asymptotes. So I'm going to put my vertical asymptotes in red. They're going to happen at the end of each period on each side, or end of half a period at each side. And those are at x equals pi over 8 and x equals negative pi over 8. And now our actual curve, we just have to remember this template, that it's going to go through the origin on its way up, like that, and it's going to come down like this over here. Now, the only thing we need to do to scale the y-axis is make sure that our a value gets achieved when we get to this quarter mark here at pi over 16. So you just pick it, doesn't really matter how high up you go. You can pick it anywhere, but I'm going to put it right about here and say that that's my a value of 10. And similarly, I'll come down the same distance and call that negative 10. Now, I can put some dots there and say, okay, here's a point at pi over 16, comma 10, and negative pi over 16, comma negative 10. And now all I have to do is kind of show that my curve is moving up like this, and then coming down over here. Tangent is an odd function, so it has this property where it has like this rotational symmetry about the origin. But there we go. That is one period of the tangent function. That total distance, of course, has pi over 8 on this side and pi over 8 on that side, which is a total of pi over 4. Just to show off, we should probably label our coordinates: pi over 16, comma 10, of course the origin at 0, 0, and negative pi over 16, comma negative 10. Now that we've already looked at tangent, it'll be a little easier to think about how we can approach cotangent. Cotangent, of course, is the reciprocal of tangent, so you can think of it as cosine of x over sine of x. And essentially, we apply the same principles in saying, okay, anytime that the sine is 0, which of course would be at 0 and pi and 2 pi and 3 pi and 4 pi, or negative pi and negative 2 pi, all those places on the x-axis, or the horizontal axis of the unit circle, is where your sine is going to be 0. And you're going to have your x-intercepts of cotangent whenever your numerator is 0, which is when the cosine is 0. So namely up there at pi over 2, it would happen to get it down here at 3 pi over 2, 5 pi over 2, and so forth. So we're going to blow through this a little more quickly than we did with tangent. But we're going to recognize that cotangent will have vertical asymptotes where the sine is 0. So that's right off the bat, right here at 0. And again, it's going to happen at pi. So let's put in some vertical asymptotes right here at 0. And let's make this a little thicker here so we can have like this yellow look right there. That's a vertical asymptote. We'd have another one over here at pi. And it's going to happen over here at negative pi as well. So go ahead and put that guy back there at negative pi. So that's for sure. So I guess we'd have pi over 2 here, and negative pi over 2 there, and pi over 4, 3 pi over 4. We can just maybe think about this portion right here. And again, this distance is pi, which for a regular cotangent function is going to be the entire period. So we think about those vertical asymptotes existing there, and of course the x-intercept, which is when the y value 0, is going to happen when the numerator is 0. So we can think about the cosine being 0 right there at pi over 2. So we're going to have an x-intercept there. Now, this is what kind of gets a little bit interesting here. Again, if we had a y value of 1, let's say right here, and -1 down here, think about the cotangent up here in the first quadrant, right here, at pi over 4. The cotangent is going to be 1 because it's going to be the sine over the cosine over the sine, which is root 2 over 2, over root 2 over 2, which of course will be 1. So at pi over 4, we're going to have a y value of 1. So we can put a point there. And then by the time we get over here into the second quadrant at 3 pi over 4, the y value for cotangent would be the cosine, which is negative root 2 over 2, over the sine, which is root 2 over 2, and that value is going to be -1. So by the time we get to 3 pi over 4, we're going to have a y value of -1. So we can just put a point there. And basically, we can place some connected dots here. It's kind of a very similar look to tangent in its curvature, but it's going to have this kind of look down here. And then again, this would just get repeated for each period. So we now have a second period drawn where there would be a y value, 3 y values that we can find real easily. This would be -3 pi over 4, comma 1. This would be negative pi over 4, comma -1. Again, negative pi over 4, that would be down here, pi over 4. And of course, your sine is going to be negative, but your cosine is going to be positive. That's why this is negative. And -3 pi over 4, that would be all the way over here, where both the sine and the cosine would be negative, so the ratio would be positive. So that's a quick look at what a basic cotangent kind of looks like. Again, this is one period here. There's a second period drawn for you there. But if you just have this, remember this template that a cotangent sort of has this look where it comes down next to the y-axis, kind of has a negative slope to it the whole way. And just remember that as a template for a basic cotangent when the b value and the a value are both 1, and then we can tweak it as necessary. So we will do one example with cotangent, and I've got an a value of 5 and a b value of 2 pi over 3, so that's the first thing I want to do is go ahead and identify those. A is 5 and b is 2 pi over 3. And so our period, just like we did with tangent, is going to be pi over b, which in this case is pi over 2 pi over 3, which is pi being multiplied by 3 over 2 pi. Pi's are going to cancel out, and we get 3/2. So the period for this particular function is going to be 3/2. Now, what we have to remember is for a cotangent, we see an entire period over here to the right of the y-axis. So I'm going to go ahead and put 3/2 right here, and it would probably be good to get half the period, which of course will be 3/2 times 1/2, which is 3/4. And we could even go so far as to get a quarter period, which will just be half of that, which will be 3/8. So 3/8 will be right there. And then this guy, of course, is just going to be 3. We've got 1/4, 2/4, 3/4, 4/4 of our period. So 1/4, 2/4, 3/4. I just need 3 of these guys. So that's going to be 9 pi over 8. Or, I'm sorry, 9/8, not 9 pi over 8. All right, so again, our template for a cotangent curve is that those asymptotes occur right on the y-axis. And then again, after one period, the distance of one period away from the y-axis. And we've got to assign some values to our y-axis. So we have an a value of 5 here. So I'll come up and put a tick mark at 5 and -5. And recognizing, again, that cotangent sort of has this negative slope the whole way down. It's going to have this kind of look to it. So I'm going to put some points there. We're going to cross the axis, the horizontal axis, halfway through. And we're going to have our a value at 1/4 of the way through, and the opposite of our a value 3/4 of the way through. So now we just play connect the dots and give it that kind of look there and this kind of look there. And that is exactly one period of a cotangent curve for this particular function. And again, 9/8 comma -5 for this point right here, 3/4 comma 0, and 3/8 comma +5. And we could even toss in the equation of our vertical asymptotes, which is x equals 3/2 and x equals 0. So there's the basic template, the idea that a cotangent curve kind of comes down next to the y-axis. The tangent curve, remember, would be up through the y-axis with half the period on this side and half the period on that side. But that's pretty much everything you need to know for tangent and cotangent graphing.